Here are the review answers for the final exams for 24-26. I have only tried to explain what is really necessary. So just go through it and try to understand. So that is question number 1, 2.62 Hertz. Because K is m omega squared. So cos omega t, and you could put plus phi, where phi or theta is the initial phase angle. Make sure you understand the formulas for kinetic energy and potential energy, and also that for total energy. Remember that the frequency or time period does not depend on the mass of the pendulum. Again, Vmax is A omega, where A is the amplitude, but this time we have to calculate the amplitude using the fact that the arc of a circle, this is the arc of a circle, is radius multiplied by the angle. But the angle is in degrees, and that's why it's converted into radians by multiplying with pi by 180. Well, the total energy is calculated just as before. So notice that two lengths are given. The first length is given to find the mass per unit length, because 90 centimeters has 3.6 grams. and it's the second length that is actually the experimental one. Of course, the overtones are just integral multiples of the fundamental frequency. You got to know I naught. I naught is 10 to the negative 12, which is the threshold of hearing. First you got to convert from decibels into watt per meter squared. You get 1. And there's only one engine working, therefore it's 1/4 of that. And now you got to change this into decibels again using the same formula. The velocity at any temperature T is V naught plus 0.6 times the temperature, but it should be in Celsius. So it's 21 degrees Celsius. So you got 343.9 meter per second. Here we had to find the length of the pipe, and so after finding the wavelength, I just noticed that it's an open pipe. So after you know that the fundamental frequency or fundamental mode of vibration in an open pipe is going to be something like that, with the antinodes at the open ends. So we know that this is lambda by 2, and so the length is equal to lambda by 2, the length of the pipe. So therefore the length of the pipe must be lambda by 2, which is 1.31 divided by 2, which is 0.655 meter. Now, in order to find the intensity, always remember you have to consider that there is a positive 1 coulomb kept at that point. So in this case, you have the positive 1 coulomb kept at the midpoint. Find the force on that one due to both. Look at the directions. In this case, both are in the same direction. So add them up. You also got to remember that K is 9 times 10 to the 9. Some slight mistake in the calculations now, which I corrected here. Sigma is the surface density of charge, which is Q by A. That's the permittivity of free space. Whenever capacitors are connected in this way with nothing else between them, they will be in parallel. So the capacitances are given, the voltages are given. First find the charge on each one, and then the total charge divided by the total capacitance will give you the common potential. That was the difference in temperature, so you got to add the initial temperature to get the final. Take care of the units here, and remember that 1 kilowatt hour is 1 unit. That's what the electricity company charges you for. So he'll be changing the watts into kilowatt hour. So the minute is changed into hours here. Just remember that when they are in oh, that is a mistake. Hold on. Yeah, that's right. In for the case of capacitors in series, it's 1 over C is 1 over C1 plus 1 over C2. I'm right. I had a small confusion. But for resistors, remember that it's the other way around. Okay. And whenever they are in series like that, the charge will be the same. In parallel, the voltage will be the same. That's very important. Now in parallel, remember that the voltages are the same. Yeah, I remember that the ratio of the voltages across a capacitor will be the same as the ratio of the charges. Check if this formula is on the formula chart. This is the small resistance to be connected to change a galvanometer into an ammeter. First you have the ammeter in the circuit, and because of its resistance, the current is going to be a little bit less than it actually is. So set up an equation using Ohm's law. I is equal to E divided by total resistance, and we know that E is going to be the same with and without the ammeter. So make two equations. This is the first one. And the second case, we got to find the current, but this time there's no 63 ohms. So that's the second one. I've divided the equations. 2 divided by 1, and the e's will get cancelled, and try to find so it's 5.51. Oh, this is where I think I made the mistake. So that's in series, okay. Energy of a capacitor is 1/2 CV squared. Oh, okay, I had corrected it. In parallel, you just add up the capacitances. Now you have to find the energy across each one. And add them up, or take the equivalent and just find it this way. Now this 18th question requires a good idea of the directions. there are two magnetic fields. One is the magnetic field due to the current flowing through the wire, which is BW, and the other is the magnetic field due to the earth. The magnetic field due to the earth has to be resolved along BX and BY. That's the magnetic field of the earth. Cos 37 gives you BX, and that much sin 37 gives you BY. Take the resultant of the Y component first, and then find the resultant. So this is because the number of turns and the area are the same in both cases. So that is the current through the transmission lines, power divided by the voltage. And to find the EMF at the generator end, obviously the EMF is going to be higher, and it's going to be the output voltage plus the voltage drop down the lines. So that gives 47.67 kilovolt. The power loss by power total is power loss is I squared R, and the power total is going to be I squared R, which is lost, plus the power that reaches the town, which in this case is 30 megawatts. So 30 times 10 to the 6. On calculation, this is 0.0559, which is 0.0559, which is about 5.6% wasted. That is the inductive reactance, and IRMS is going to be VRMS divided by the inductive reactance. That was another calculation mistake. In these problems, you have to be really careful about the calculations. Calculate the impedance, then tan phi, which is the phase difference, is XL minus XC by R. It could be negative, and the negative shows that it's lagging behind by 7.62. IRMS is VRMS by the impedance. 0.082 ampere. $24 and $25 are not required because I had not made you do problems on these two. Now you have to be really careful about convex lens and a concave mirror. Both have real focus, F is positive, while a convex mirror and a concave lens have virtual focus, so negative focal length. Here I'm just trying to show you how that image would be formed. It is a virtual image. This is a convex mirror, remember, and it can only produce a virtual image. And the distances appear to be correct, because if the focal length is 10 centimeter, which is this, and this came out to be negative 6.67, that's fairly right. This is a convex mirror, because although a concave mirror can also produce a virtual image, its virtual image is bigger than the object. In the case of a prism, we just apply Snell's law at both the faces, and then the formula that is used in addition in this case is that R1 plus R2 is equal to the angle of the prism. And remember, this is an equilateral prism, that's why A is 60 degrees. So that's the application of Snell's law at the first phase. Well, that's not I2, that should be R1 actually. Okay, I'm going to correct this. It's I1 and R1, so I need to correct all of that. Yeah, that's R1. Now R1 plus R2 is A, so from that you can find R2. And then once again use Snell's law at the second phase to get I2. Remember that the power of a lens is 1 by focal length, but the focal length must be in meters. So if the power is in diopters, focal length will be in meters. It's a plano concave lens. So the plane surface has infinite radius. That's a lens maker's equation. It's taken as negative because it's a concave lens. Now just find the angles of refraction for both the wavelengths and find the difference. When it talks of maximum orders that can be seen, theta should be 90 degrees. Here the conditions are not reversed because two reflections take place, and both take place when light goes from less denser to a more denser medium. So the condition for brightness is path difference is equal to m plus half lambda. Well, I'm trying to show that, at both the reflections, it's going from, first reflection is going from air into the coating, and second is going from the coating into the lens. And both take place as it goes from less dense to more dense. Obviously, the person is far-sighted, and farsightedness is corrected using a convex lens. Therefore, we got to get F as positive. .57 diopters is a big power. Again, here power is given in diopters, so the focal length will be in meter. We'll have to change it into centimeters. Magnification is minus FO by FE. One light year is 9.46 times 10 to the 15 meter, because it's the distance traveled by light in 1 year. So that will be 3 times 10 to the 8 multiplied by 24 times 3600 times 365. That's the number of seconds in 1 year. So that's how you get 1 light year as 9.46 times 10 to the 15 meter. Now this question has to be done really carefully, because kinetic energy relativistically is gamma minus 1 mc squared, and then it's all math. It's better to first make gamma the subject and get its value, as I've done. And here again 105 and 938 are both in million electron volts, so it's just a ratio. And remember that the rest mass energy of the electron is 938 million electron volts. You need to know that. And now, since we have the value of gamma, try to put it into the formula and make velocity the subject, where you have to be really careful. Now the S frame is the Earth, and the S prime frame is the first rocket. So the velocity of the first rocket will be v. In the second case, when it goes in the opposite direction, the only difference is it's going to be negative 0.87 C. The formula is the same. From the Earth, it's at rest, so divide 10.6 light year, that's distance or length, by 0.960 to get 11.04. Now the time from the spacecraft should be less. Therefore, delta T naught is what we're trying to find, is delta T times root 1 minus V squared by C squared. And of course, d, you will get back the original velocity. It's L divided by delta T naught. And finally, this has taken me about 6 to 7 hours, so I hope you make full use of this. Thank you.